All right, good afternoon. Okay. Now let's hit the lights. Okay. All right. Well, let's see who's here. I know there's a lot of people gone with sports today. But let's see. All right. James.
He's here. He just had to run to the restroom.
Okay. Joanna.
Here.
Ashley.
Ashley's not here. She has soccer.
All right. Thank you. Marissa.
I'm here.
Jerica.
Here.
Courtney.
My throat hurts really bad.
Jada.
Here.
Autumn.
Here.
Matthew.
Here.
Weston.
Here.
Chan.
Here.
Kelly. Porter.
I thought he was.
Here.
Ronald.
Boom.
Here.
Kayla. Tobias.
You're seriously gonna love
Here.
your friends.
Nathan.
I'm here.
And Rebecca.
Here.
All right, so absent we have Kayla, Kelly, and Ashley. Okay, so the next thing is all right. Let's see here. So the good news is for me is that I got to try to do my day without crutches. So that's good, but the bad news is I'm still as slow as ever. So, all right. All right, so those of you that had me last year might remember the random name chooser that now doesn't work in this version of Smart Notebook. So I'm now gonna do it using these wheels of fortune here. So look and make sure your name's on there and that it's spelled correctly. Or if if your name is James and you want me to call you Jimmy, then we can change that too. So everybody's name okay?
So Ronald is Trey and
Okay.
Porter is Seth.
Ronald is Trey. All right, Porter is Seth. And that's Trey.
Why?
Okay.
And Mr. Strong, if you don't mind, could you put me in there as Jimmy instead of James?
You bet.
Thanks.
Sure. All right. Anything else?
Jerica goes by Caroline.
Jerica goes by what?
Oh, Caroline.
Caroline. Like that? Like Sweet Caroline?
Yes.
All right. Anything else? Okay, very good. Actually, that's kind of one of my pet peeves when people spell my name wrong. But anyway. Okay, so we'll do that. And then we've got, so today we're on 2.2, the limit laws. So any questions or comments or concerns before we get started? Okay. All right, let's see. So you can see me, you can see the screen, everybody's good? Yes? Okay, good. All right, so yesterday we left off and we were talking about the behavior of each of these functions as x approaches 0. And so the first one, the greatest integer one, that was the step function. And so because there was a jump there as x approaches 0, then we said that the limit does not exist. And so this is the symbol, this little backwards e, it exists, and then with the slash through it doesn't exist. But the book doesn't use that symbol. That's just when I write my book that I'm going to use that all the time. Okay. All right. So someone was in the middle of answering this one when we got dropped. So 1 over x. What is that reciprocal function? What does that look like? Can anybody draw it in the air? Okay, so one side goes up and the other side goes down. All right, and so, but it actually goes to infinity. So that was one where we said it was too large for the limit to exist. So that one doesn't exist. All right, now, so y equals sine x. What does that approach as x approaches 0? What does the y value approach? All right, let's use our little wheel. Okay, so that will be Matthew. What does sine x approach as x approaches 0?
0.
0. Okay. So there's now it does oscillate, which means it goes up and down. But as x approaches 0, the y value approaches 0. It doesn't like oscillate crazy, and so even though when we talked about that an oscillating graph might make it so the limit doesn't exist, that's when as you approach, say 0, it keeps going up and down. But this one, it actually does approach 0. Okay, so good job. All right, any questions on those? Okay. All right. Now, these are the limit laws that are in the book. Now, I don't really think you need to write these down. I don't even think you need to memorize them or anything. You might just know that they're in the book, but these pretty much work the way that you think that they should. So once you start doing limits, you'll just sort of do these naturally. Okay? There's nothing really amazing. This just says, look, if you're taking the limit of different functions, you can just add the limits. Or if you're subtracting, then you can subtract the limits. Or if you have a constant times a function, then it would be the constant times the limit. Or if you have the product of two functions, you do the product of the limits. Or the quotient of two functions, you do the quotient of the limits. Or a function raised to a power, it'll be the limit raised to the power. Or a root of a function, you do the limit and then the root of the limit. Okay? And so it really, like I said, once we start doing the limits, all these things you'll do naturally. Okay, you don't really need to. Just know that it's legit. Okay. All right. So, for example, let's say that x is approaching a certain number. Okay. So what the limit law says is that we can take each limit separately. All right, but really, in real life, you don't do that. You don't rewrite it as three limits. All you do is you just take and you plug in the number for x and then work it out. Okay? So whatever c is, you plug it in, and so it'd be c cubed plus 4c squared minus 3. So like, let's say if c is 5, then you would plug in 5 for the constant and then work it out. Okay? You don't really need this step right here where you're rewriting it. It'll just comes naturally. Okay? All right? So see if you can, calculate this limit as x approaches 2. All right, Joanna.
21.
21 is correct. Great job. Any questions on that? All right. Super. You just plug in the number. Okay. All right. So now here we have a quotient. So if x is approaching some number, then again, you can just plug it in. It doesn't matter that it's a quotient. Okay. You just, whatever the number is, you plug it in and then you just work it out. Okay. And so try this one. Oh, you guys at White Mountain campus, I know you met Miss Heaster last week, right? Renelle Heaster?
Yeah, we met her.
Yeah, so anyway, so just so you know, she ordered you guys a longer cord for that touch 10 unit so that you can just hopefully sit at your regular desk and not have to, have one of you up there. Okay? So
Thank you.
You bet. Just wanted to let you know. All right. So, all right, Chen.
Negative 21.
Negative 21 is correct. Great job. All right. Any questions on that? Okay. All right. Now, so even when we have a square root or something like that, that doesn't matter. Whatever the number is, you just plug it in and then you work it out. So whatever C is, you plug it in and then just get the radical. Okay. All right. So try that one. All right, Rebecca, when you've got it.
Um, 3.6.
3.6. So square root of 13. Is that what square root of 13 is? Sounds about right. Now, if you are going to do it as a decimal, give me 3. Take it out to 3 decimal places. So let's say, so 3 point. So can you give me 3 decimal places?
3.606.
606. All right. Any questions on that? Or you could just said square root of 13. Either way. Okay. All right. So the limit of a polynomial function, that's what we've been dealing with mostly, is found by substitution. So if it's just a polynomial, you can just plug in what x is approaching, plug in that number, and that's it. That's the answer. The limit of a rational function can be found by substitution if the denominator is not 0. So whenever you get a 0 in the denominator, that means you got to do it a different way. Okay? It doesn't mean that the answer is undefined necessarily. It just means you have to do it another way. Okay? Okay. All right. So then the idea is first you try to plug in. Okay? So first you try to plug in -1. Everywhere there's an x, you plug in -1 and then see if it works out. Okay? Now here we got 0. Now 0 over 6, which is 0, that's a perfectly fine answer. So the answer is 0. It's when you have a 0 in the denominator, you have to do something else. Okay? All right, so try that one. All right, Chan again.
-1/5.
Negative, oh, did we not have, oh, there we go, -1/5. That is correct. Good job. Okay? Any questions on that one? All right. Okay, so once you plug in, if you end up with a 0 over 0, then that's when you try to factor and cancel. Okay, so we've done these. So here, so like if you have, you try to plug in 1 here, and you get 1 plus 1 minus 2, so that's 0 over 1 minus 1 is 0. So you get 0 divided by 0. Okay? So when you get 0 divided by 0, that's, or anytime you get 0 in the denominator, but especially 0 over 0, then that's when you look to see if you can cancel a common factor. All right? Because that's what's going to happen most of the time, is you'll be able to cancel a common factor. Nope. Okay. All right, so you factor the numerator to x plus 2 times x minus 1. You factor the denominator, you factor out an x times x minus 1. So when you cancel the x minus 1s, on the graph, what's going to happen where x is 1? What happens on the graph where x equals 1? Where you have a factor that'll cancel.
You have an asymptote?
Good guess. It's when you have an asymptote when you just have a 0 in the denominator that doesn't cancel. When it does cancel, it doesn't produce an asymptote but a hole. That's when you get a hole in the graph. Okay? All right, but actually, that has nothing to do with what we're doing right now. It's just, So, so when you cancel the x minus 1s, then you're left with this. Okay? So now, as far as calculating the limit, now we try plugging in 1 again. And so then when we plug in 1, we're going to get 1 plus 2 over 1. So the answer is 3. Okay? All right. So just kind of showing the graph, when x is 1 here, see, you have a hole in the graph. But that's not what the limit is. The limit, as x approaches 1, see, as x approaches 1, the y value is going to approach 3 from both above and below. So the limit is 3. Okay. All right, so try this one. Some guys have all the luck, all right?
This rigged.
So, Chan, what do you have this time?
I got 0 over 0.
0 over 0, okay? So that can't be your final answer, though. So 0 over 0, so then what you look to do is try to factor and cancel. So, Chan, have you had like an amazingly lucky day today?
Not really.
Not really? Well, it's going to happen. Everything's going to work out your way the whole rest of the day. You just watch.
Thank you. I got 9 over 4.
Okay, so then you factor the numerator and factor the denominator, and so the x plus 2's cancel. So that means that x equals -2, you would have a hole in the graph. Okay? But now, to get the limit, you go ahead and plug in -2, and so you'll get -9 over -4, which simplifies to 9/4. All right? Great job. Any questions? Uh-oh, I knew it. Okay. Let's see if we can. All right, let's see if that helps. Oh, there it was. Okay. All right. So now this is using calculators and computers to estimate a limit. So we have actually done this already, where I showed you where you can use a table or a graph to calculate limits. So if substitution yields a 0 in the denominator and there's no obvious common factors, another technique to finding the limits is to use a table or a graph on the calculator. All right. So where we were, when we used the table or graph before in the last section, you can always do that. So if you ever have a complicated limit and you have no idea what to do and you've forgotten the algebra trick that I taught you or something, you can always use your calculator as sort of a backup, okay, to look at a table or a graph. All right, now, so like this one right here, I'm actually going to teach you later an algebra trick to do this one, okay? But for now, let's suppose you have no idea what to do here, other than you plug in 0 and you get the square root of 9. 3 minus 3 is 0 over 0 squared is 0, but it doesn't factor or cancel, okay? So then what do? Well, like I said, I'm going to teach you later how to do these, but for now, what you can do is try to look at the graph or the table. So I want you to see if you can do that. So put this into the y1 in your calculator, and then either look at the graph as x approaches 0, or plug in values on the table close to 0. So like 0.01, 0.001, negative 0.1, negative 0.01. And see if you can figure out what y value it's approaching, either from the table or the graph. All right, Tobias, when you've got it.
Okay, so I don't know if like I'm graphed it wrong, but I'm just getting a straight line across. Like, is that supposed to happen?
Okay, so I mean, I don't know if it's a straight line. I don't think it should be a straight line. Do you have parentheses around your numerator?
Yeah, I have parentheses around the whole thing.
Okay. So what value as x gets closer to 0, what do you get? See, it could be pretty flat in that area.
It's like, hold on.
So you could like trace it.
So I got 0.15.
0.15. Okay. So let's see what we've got here. Let's see. So from just using the table, we got it to level off at 0.167, and then it actually does go pretty constant there. All right. So let's see why we didn't get 0.15 though. I'm curious. Let's look at the graph. Well, let's see. Wait, do I have this graphed anywhere? No. All right, let's go ahead and do it by graphing since that's how you did it. is this not letting me? Okay. So that's the function I need to put in there. So parentheses, square root x squared plus 9. And then get out of the radical, minus 3, close parentheses to close the numerator, divided by x squared. All right, and so then if I graph that, okay, so I've got a weird window, I can tell. So let's just try a zoom standard, zoom 6. Okay, it does look pretty straight in that part. So if we trace that, see, is x, oh, you were giving me the x value. See, the limit is the y value, okay? So the limit would be the 1.1665 or 0.167, not the 0.15, okay? The y value is the limit, okay? Does that make sense?
Yeah, I actually zoomed in and then I ended up getting 0.167.
Okay, all right, good. Yeah. Okay.
Hey, Mr. Strong.
Yes.
So when I graphed it with parentheses around the equation, it graphed like a straight line. And then when I didn't use parentheses, it came up with like another like graph.
Yeah, because you have to have parentheses around the numerator. Otherwise, your 3, it's just 3 divided by x squared. See, without the parentheses there, the x squared doesn't go under the whole thing. It just goes under the 3. So that would be the wrong graph. So you do have to have parentheses around that numerator. Now notice I didn't type in this set of parentheses under the radical, but that's how it has to show it here. But whereas in the y equals, it didn't have that set of parentheses. It just shows it under the radical, the x squared plus 9. But that's the same thing. Okay. All right, any other questions or comments on that one? So the point is no matter how difficult the function gets, how crazy it gets, you can always use a graph or the table. See, let's go to trace. Oh, no, not 0. Well, that's all right. We've got what we wanted. Okay. So we talked about canceling a factor, but sometimes it says if substitution yields a 0 in the denominator and there are no obvious common factors, another technique to finding the limit is to multiply by the conjugate, simplify, and substitute. Okay? So this is a new algebra technique, to multiply by the conjugate. So like if you have a radical, especially, then you multiply by the conjugate of the term containing the radical. Okay? So here, so we're actually going to create, by multiplying by the conjugate, it actually makes it so we can substitute. So what you do, see this term, again, you can try plugging in the 0, but then you end up with the square root of 100, which is 10 minus 10 over 0, so 0 over 0. So that doesn't work. There's nothing that you can factor, so the next thing that you try is multiplying by the conjugate. So the conjugate of a radical minus 10 would be the radical plus 10. Okay? You don't change the sign inside the radical. Okay? So the conjugate of the radical. Now, you actually do not multiply out the denominator because we want stuff to cancel. So just leave it. But the numerator, if you have a radical times the radical, well, it's just going to come out with radical. So you'll have x squared plus 100. And then when you multiply conjugates, the outer and the inner products cancel. So you're left with minus 10 times 10 is 100. So again, don't multiply out the denominator. Well, now the hundreds cancel, which is wonderful because then all we're left with is x squared. And so now the x squareds will cancel. And so when everything cancels in the numerator, you put a 1. And so you'll have 1 over the radical plus 10. Now you try plugging in again. Okay, and so when you plug in 0 for x, you get the square root of 10, square root of 100, which is 10. So 10 plus 10 is 20. So your answer is 1/20. Okay. So again, when you plug in, if you get 0 over 0, and you can't think of how to factor, look to see if you can multiply by the conjugate. All right, so try that one. Now, anybody want to see the example again? Yeah? Okay, so I'll just go back and show that. All right, so Nathan, when you've got the answer or if you get stuck, let us know.
1/6.
1/6. All right, so let's see, there's the conjugate right there. So then you get x squared plus 9 minus 9. When you multiply that out, the 9's cancel. The x squareds cancel. You plug in 0, and you get 1/6. Great job. Okay. Any questions? All right, excellent work. Okay, so just kind of summing up what we've done so far, okay? And actually where we're going to go to next. So the first thing you try to do is substitute in whatever the value is approaching, okay? You just plug it in, all right? If you get an answer, great. All right, then if you get 0 over 0, then try to factor, cancel, and substitute again. If you have a square root, multiply by the conjugate. All right, now, the next method I'm going to show you, we're probably not going to have time to finish it, but I'll start it, is what's called the sandwich theorem. And so sometimes we'll use that. And then, but if none of those things work, you can always do the table or the graph from the calculator. Okay. All right. So now is story time. So I don't know if I'm going to get through the story, but I'm going to start it. So does anybody remember the song that the genie sings at the beginning of Aladdin? What song does he sing?
I don't know exactly.
Never had a friend like me.
That or earlier. That he does sing that later. But he sings a song called Arabian Nights. Okay? And anyway, the beginning of that song, he talks about that like Ali Baba had some 40 thieves, Sherazade had 1,000 tales. Okay? Anyway, Sherazade, or Sherazade, depending on how you say it, was actually this beautiful princess. And she lived in this kingdom a long time ago, and there was this sultan. And the sultan, what he would do is he would find some pretty young maid in the kingdom, and he would marry her, and then they would have their honeymoon, and then the next morning he would have her killed, so that he'd find a new bride every day. Okay? Well, so Sherazade, not only was she beautiful, but she was really smart too. And so what she did is, after she'd married the Sultan, she told him that she had a story to tell him. And so what she did is she would tell him a story, and then when it got right to the, interesting part and, the cliffhanger, she would say, "I'll tell you the rest tomorrow." And so then the Sultan would spare her life because he wanted to know how the story ended. And so then what she would do is she would finish the story, and then she would start the next part of the story. And so she did that. And then again, he would say, well, what happens next? And she'd say, well, I'll tell you tomorrow. Well, so one of her stories was about, and it was like Aladdin and Sinbad the Sailor and all these, Ali Baba and the 40 Thieves and all of these things were Sherazadi's tales. And so 1,001 nights she did this until the Sultan fell in love. Okay? And anyway, well, one of the stories that she tells is about a sister, a brother and sister, and the sister comes to this magician and she says, something has happened to my brother. That he was a merchant and he went along this caravan and he was waylaid by this evil sorcerer, this hermit, that lured him off the path, promising him great goods and treasures, and then to punish him for his greed, turned the brother into a grain of black rice, and then tossed him into the sands of the desert. And the sister says, how can I find my brother? And so the magician thinks about it for a while, and then he gives her these two huge platters that are magical and throws them into the desert. And he says to wander back and forth between these the platters, because the black grain of rice that is her brother will always be between these two platters. And so if she can find that black grain of rice, then the magician can restore the brother to his human form. And so the idea is that so she goes back and forth between the two platters, and meanwhile the platters start getting closer and closer and closer together. And so she keeps going back and forth, and finally, well, do you want to know what happens? Anybody want to know? Well, I'll tell you tomorrow. All right. So that's how we're going to end today, is with Sherazadi's Tales tomorrow. So we'll pick it up and then actually relate this story to calculus. Okay. So let's see if I've got it. So this is like